Hey, I'm Jeremy. I work for Juxt, a software consultancy that is passionate about closure. 3 years ago, we released XTDB, and this talk is about our motivation and vision for baking in a bitemporal model of time at the lowest levels of XT's current and future architecture. For the avoidance of doubt, this talk is not about the philosophy of time, and neither is this talk about time series analysis over non-transactional workloads, or advanced distributed systems concepts like causal consistency or logical clocks. To start with, let's consider a very ordinary-looking relational database table. Most implementations of the relational model will allow users to arbitrarily modify the rows in that table. By default, after any modifications are made, the old version of the table is essentially unrecoverable. In other words, the users have destructively mutated the state of the table. This is sometimes referred to as update-in-place semantics, or place-oriented semantics. From an operational perspective, perhaps the biggest problem with update-in-place databases is that when things go wrong, like when there's a bug in the code that generates the modification, there is usually no real recourse to recover the situation from within the data plane. Like there's simply no support for rollbacks or a concept of undo beyond the scope of a single transaction. Instead, data may have to be recovered by accessing backups or logs, which is well outside the realms of the query language. And from an application design perspective, business requirements can often demand storing the changes to the records in the database in a way that can be made visible via querying to the application, such as for auditing or versioning purposes. But update-in-place databases force the developer to carefully design the schema accordingly. Typically, such a schema design will avoid mutating any existing rows in the table, and instead applications will append rows that describe the change and the new state of the record. But this type of append-only design immediately makes various basic query features like joins more complicated. So it seems this concept of update in place can be a problematic foundation to build upon if it can on the one hand so easily result in broken databases, and on the other hand force the complexity of append-only semantics to exist only in the schema. But what is the alternative, and why are we as an industry, for the most part, still stuck in the old world of mutating tables? Well, before I try to answer that, I want to quickly explain how I've ended up forming strong opinions on this topic. About 10 years ago, it dawned on me that the world relies far too heavily on ad hoc emails and other inefficient forms of tacit knowledge, and I felt inspired to build software that could radically improve the status quo. I initially had the idea of creating a mind mapping tool that could support seamless collaboration, a tool that didn't lock data away behind siloed applications, and instead could support a myriad of user interfaces. I then realized that, before writing too much code, I really ought to choose a database that was well suited to the problem. Consequently, in the course of getting to grips with much hyped NoSQL databases like CouchDB, I discovered that Lotus Notes, a once beloved corporate email client, was in actual fact a local-first application platform that had pioneered with almost exactly the same ideas well over 30 years ago. This was back in the dial-up era and in the early days of public key cryptography. Crucially, Lotus Notes is built upon a foundation of decentralized multi-master replication of version documents with complex and evolving applications embedded inside. Digging deeper still into the broader history of the field, I found myself resonating with the ideas and motivations of great visionaries of the past, people like Vannevar Bush and Doug Engelbart, who saw the potential for technology primarily as a means of collective intelligence amplification. And ultimately, these same ideas motivated me to study Datomic, with its flexible graph-like schema, data-log query language, and its rather novel, value-oriented approach to avoiding update-in-place semantics called the epochal time model. I then spent time prototyping various user interface ideas in Clojure using DataScript, and finally I joined Juxt, who it turned out had been building the database I had been searching for all along. But let's return now to the practicalities of how to fix the update-in-place relational model. An append-only table with created at timestamps isn't a bad place to start, but there is a huge design space beyond that. Unsurprisingly, it turns out that people have been reflecting on this question for a long time. Various designs for a first-class history of data in databases have been contemplated since even before the first publications of SQL, and such thinking arguably reached peak excitement in both academia and industry around the late 1990s. Since then, storage has grown almost infinitely in abundance, but the two most pressing motivations have not changed. Firstly, users want to maintain a full set of auditable changes across all records, and second, they want to model the validity of their records so that they accurately reflect their domain. Bitemporality, as comprehensively defined by Richard Snodgrass, captures these two ideas in a single concept, but let's build it all up slowly with some examples. To help us out, we can think about it all in terms of SQL, and we can draw on the little-known or appreciated features of the SQL 2011 revision of the ISO standard, which extended SQL with bitemporal semantics. Somewhat confusingly, the SQL spec refers to the audit log-like nature of transaction time as system time, and refers to the domain interval modeling notion of valid time as application time. And if you're into the world of event streaming, you may even be more comfortable thinking about other synonyms for these same ideas, like ingestion time and event time. And there are plenty of other popular synonyms too, but I digress. I would like you to first of all consider this example of two diagrams that have been created in the context of data warehousing with Postgres. And unfortunately, Postgres hasn't yet implemented the SQL 2011 temporal functionality. On the left is a bog standard relational table about the price history of a single product. Note that there are 4 timestamp columns representing the intervals for the 2 time dimensions, and we are using the term registered time instead of system time. And then on the right, we have a 2-dimensional plot of regions of that same history, with the colours across both visuals corresponding to historical regions of equivalent prices. This kind of modelling is often necessary to satisfy fundamental auditing requirements. It allows users to confidently produce the answer to a time travel question like, what do we think the price was on the 1st of February as of the 28th of February? The valid times could even represent proposed times in the future for when those prices are intended to be effective. So now we've seen a time travel query on a single table, what could it look like if we wanted to join this bitemporal view of product price with a very similar bitemporal view of VAT that is in turn stored in its own table with a potentially very distinct bitemporal history? Well, the example suggests that we could create a table or view to help us. First, we extract all the valid times across these tables, then link the products to those partitioned intervals, and then finally we can perform the join. But of course this solution is only taking valid time into account. What if I wanted to include registered time in this join as well, so that I can run my audit queries? And then what if I wanted to join across more than 2 tables like this? Clearly this is painful, and there are countless developers working across all manner of organizations today who are maintaining SQL that looks almost exactly like this in production. And it's all bespoke, potentially full of bugs, and typically far away from efficient to store and query. So how does SQL 2011 attempt to alleviate some of this pain? Well, the standard defines application time as any user-defined period in a table. For instance, if we have a table of employees with a start date and an end date, we can declare a period in the DDL. Now we can update that table, or delete rows in that table, and then we can use Allen interval predicates to simplify queries over the periods, such as for point-in-time time travel queries and for temporal range queries. As for system time, it is defined as a set of system-maintained start, end, and period columns, also declared through DDL. And now we can make non-destructive, auditable updates automatically, without having to invent our own append-only semantics. And for the most part, users don't have to think about system time when writing queries, because as of now is the default context. This enables users to query a globally consistent snapshot of the table, giving users repeatable reads, and audit queries. Bitemporality in SQL 2011 then is simply a combination of these 2 orthogonal time dimensions, and the DDL very much reflects this, showing the full combination of all 6 additional columns. So now users can ask their time travel queries with relative ease, and more importantly, they don't have to worry about getting all the implementation details for this correct in their application and schema. Naturally, this begs the question that given SQL now has these powerful features, why isn't everybody just using them routinely right now? Well, it seems to me that the adoption of the SQL 2011 bitemporal features by database vendors has been underwhelming. Undoubtedly, a large part of the problem is due to the impact on schema management, where changing foundational behaviors for things like foreign keys, primary keys, and uniqueness constraints is non-trivial, and for users, what would ordinarily be straightforward SQL schema migrations suddenly become a real challenge. Another complexity is that temporal tables naturally imply that lots of historical data is being kept available for online transactions, which for most non-analytic database architectures is inherently problematic, since they were created long before the advent of cloud storage. As an interesting aside, it's worth appreciating that Postgres initially aspired to be a system-time temporal database, and also that system time is a widely understood concept across many databases, but is generally regarded as an infrastructure-level concern in support of read snapshots. Over the years, people have developed draft patches and extensions for adding bitemporality to Postgres, but nobody has thoroughly solved the fundamental architectural challenges. In general, it seems that SQL 2011 is not something that can be easily bolted on as an afterthought. For XTDB, we have, up until now, attempted to bring bitemporality to a wider audience from a completely different angle, following closely in the footsteps of Datomic. The currently released version has been optimized for running point-in-time bitemporal data log queries that execute on top of embedded RocksDB indexes. Transactions are non-interactive and rely on a single writer in favor of infinite horizontal read scaling. In XT's data model, every entity in the database has a bitemporal history maintained automatically, and entities are expressed as versioned documents that get indexed as EAV triples without any upfront user-provided schema or DDL. 2 temporal indexes exist to support ad hoc point-in-time filtering, and data can be evicted from the otherwise immutable system when really needed. For the next major release of XT, we are working on a new hybrid transactional analytic processing HTAP architecture that separates storage and compute using Apache Arrow at the foundation. Storage of document-like records is enabled by Arrow's columnar format for dense unions of polymorphic types. And we have a 6-dimensional temporal index to allow for more than just point-in-time queries so that the vectorized relational execution engine can efficiently filter for visible rows. Our current engineering focus is to create a SQL dialect based on the published standards, but with the dynamic feel of Lisp over this semi-structured and bitemporal data. Unlike SQL 2011's per table DDL, all data in XT is handled as bitemporal data automatically. To wrap up, whilst bitemporality can be a very obvious requirement to consider in certain domains, it should also be something that most users can feel free to safely ignore until the point that they actually need to care about it. But if a user realizes tomorrow that they do need to care about bitemporality after all, it seems there are no easy ways to retrofit it to an existing database architecture, which is why it has to be baked in at the bottom. Thank you for your attention.